In this video, let's do another example of finding the volume of a solid of revolution. So let's consider the following region. Consider the triangular region bounded by the lines f of x equals x, g of x equals 0, and h of x equals negative 2x plus 2. Now, I feel like you probably already know what I'm going to do right now. Here come the axes, here comes the drawing. So I'm going to draw f of x equals x, straight identity function, y equals x, and we have g of x equals 0, y equals 0, and that is just the x-axis down below. And we are also going to have h of x equals negative 2x plus 2, so that will come in right here, down at a nice dramatic slope, y equals negative 2x plus 2. Now, for the record, let's establish where this region begins and ends really quickly. So, at the beginning, we have the origin 0, 0 in the bottom left corner, y equals x, and y equals negative 2x plus 2. Let's check for a moment at what point these two lines cross each other. So if I set x equals negative 2x plus 2, and I solve for x, that tells me that x and thus y as well are both equal to 2/3. And so that would be this corner point right here, 2/3, 2/3. And finally, the bottom corner of this triangular region, the one on the right-hand side, occurs when y equals negative 2x plus 2 crosses the x-axis. So that would occur when the y value is 0, and I think that we can achieve that when x is 1. So now that we have decorated this region, let's consider the surface of revolution that we get when we spin this region around the y-axis, So that means that if I take a slice at some arbitrary y value, I'm going to be spinning that region along the y-axis, giving me still a washer shape, but the washer shape now is horizontal. So this means, first of all, that the slices are horizontal, and we get one slice per y value. Each vertical y value in this region, each y value is going to give me a different washer-shaped slice of this solid of revolution. The lower y value is y equals 0 at the bottom of the region, and the y value at the top of the region, y equals 2/3, this is the uppermost y value. Now, to find out the area of the slice, let's call it a as a function of y. In this case, still washer-shaped, so the formula will still look like big radius squared, take away little radius squared, times pi. However, we have to be especially careful because the radius of this disk, the outer radius of this washer, is an x-coordinate. The radius of this washer is given to me by the x value of the point on the outermost green line. So what I will need to do is I need to rewrite the functions which are currently in the form y is a function of x, y is a function of h. I need to rewrite them so that I know what the x value is. I need x as a function of y. I need x as a function of y so that the independent variable y is an exact match for the variable of the axis that we're spinning around. Spin around the y-axis, you need x as a function of y. So, if I take f of x equals x, if I take f of x equals x, y equals x, and that can be pretty simply rewritten as just x equals y. And so here is x as a function of y. If I take y equals negative 2x plus 2, and I solve that for x, I get that x as a function of y is negative 1 over 2 times y plus 1. Here's x as a function of y. Y is the independent variable. And so now, to find the volume of this solid of revolution, I just jumped way too far. Hold on. Yep. We can integrate from the lowermost y value, 0, to the uppermost y value, 2/3, pi, the outer radius. Now be careful. I always go back and reference my picture. The outer radius is given to me by the green line y equals negative 2x plus 2, which turned into the function x equals negative half y plus 1. Outer radius squared. Take away inner radius squared. And since we're spinning around the y-axis, we'll integrate this function with y as our variable. Calculate this definite integral, and you will have the volume of this region, which was obtained by spinning around the y-axis. The key step here is to make sure that your limits are in terms of y values, and to make sure that your functions have y as their independent variable.